Okay. Yeah, so hello everyone for the new edition of the SGEB seminar, in which the Master Prize winners will present their thesis. So this year we had 3 Master Prize winners at EPFL and ETHZ. We have one winner was Saad Abdeljalil, who made a project on the projet d'intervention pour la remise en état et la conformité sismique du viaduc de l'île Falcon, which he wrote under supervision or in the MCS lab under supervision of Professor Brübüler, and also it was a thesis in partially conducted at the enterprise Emsberger at Lausanne. Unfortunately, for confidentiality reasons, he's not able to present this project. Then we have Joëlle Luu, who is here to present her project on finite element investigations of the slotted hidden gap connection for square HSS bracing members under cyclic loading, which is a novel bracing connection system. And I think you will maybe also talk about this as already implemented in some codes. So we're happy to learn more about this. It was a project conducted at the RES Lab with Dimitrios Lignos and the McGill University in Canada with Professor Rogers. And then we have from ETHZ, the Master Prize winner is Alexandre Milliet, who did a thesis on investigations of collapse resistance in tall timber buildings, where you developed a framework to investigate that under the supervision of Professor, or in the lab of Professor Fangi. So we're happy to have you present your thesis. And as we discussed earlier, I think we will start with Joëlle and then Alexandre. And questions, if you have questions during the presentations, you can already write them in the chat, and then they will address these after the presentations, or you can ask the questions orally after the presentations. So Joëlle, the floor is yours.
Mm-hmm. Do you see my screen?
Yes. Okay.
Okay. So thank you for the introduction and for giving us the chance to present our work. So I'll be speaking in English to make the presentation more accessible. So yeah, as said, I won't be able to see you, so don't hesitate to interrupt me if you have any questions. Okay, so let's dive in. The title of my master thesis is Finite Element Investigation of the Slotted Hinge Gap Connection for Square HSS Bracing Members under Cyclic Loading. So here's an overview of the presentation we'll be covering today. So I will start with an introduction and some literature review on the existing research of the topic. And based on that, I will cover the objectives and methodology used for this project. And then I will go through the 2 main chapters of the thesis, including the calibration of a finite element model against some laboratory test results and the parametric study. Then we will conclude with a summary of the project and some recommendations. So in concentrically braced frames, which are a type of steel structure, a commonly used connection to connect a hollow brace to the gusset plate is the slotted tube-to-gusset connection, shown here, which consists of slotting the HSS and inserting the gusset plate that we will call the conventional connection. And although it is aesthetic and simple to implement, this connection suffered 2 major drawbacks. The first one being shear lag effects due to unconnected portions between the elements that lead to a non-uniform stress distribution, and also a net section failure that occurs here due to the slotted tube when subjected to tension. So typical solutions to overcome these problems are either additional reinforcement plates that help to distribute more evenly the stresses, or a return weld, shown here, around the gusset plate. However, those solutions require additional design and material, so time and cost, and return welds have been proven to be unsuitable for seismic applications. So the slotted hidden gap connection, which is shown here, was developed in the 80s, which consists of notching here the gusset plate, so the welds can start in the gross section of the tube. And past research pointed that it helps to push the stress concentration away from the connection, avoiding failure at that critical location. So here's an overview of the existing research on that topic. So it started first with Mitsui, and then Martinez-Saucedo and Packer that studied the slotted hidden gap connection comprising rounded tubes. And then later, Moreau and Afifi investigated numerical models and testing in the lab of the slotted hidden gap connection, but this time including square HSS. So HSS stands for hollow structural section, with an emphasis on tensile loading. So it resulted that Afifi and co-authors developed a design methodology to construct the slotted hidden gap connection. However, for seismic applications, it is also important to investigate the connection under compressive loading, as typical compressive response such as buckling is not captured under tension. So the goals of this project is to assess the slotted hidden gap connection under cyclic loading conditions, with an emphasis this time on the compressive behavior of the connection. So to meet these objectives, a numerical parametric study is performed. So in order to create a realistic numerical model, we did first a calibration between our finite element model against some test results from a full brace tested in the lab by Moreau. So this is a picture of the tested full brace in the lab by Moreau, and this is a little bit less than 5 meters long. So the square HSS, which is here in yellow, has a width of 203 millimeters and a wall thickness of 13 millimeters. And it is made from a CSA J40 2021 Class C, and the gusset plate here in green is made from the American specification ASTM A572. So it is loaded here at the top, at the upper grip, according to this tensile dominated loading protocol. So now I will describe the assumptions made for the numerical model developed in the software Abacus. So this is a visual representation of the finite element model. So of course, we tried to replicate as closely as possible the geometry of the tested brace using the same dimensions and arrangement. So I'm not going into too much detail regarding the material, but we used a refined version of the Vos-Chaboch model to convert the tensile data obtained from the laboratory tests into more suitable data for cyclic applications. So the compressive behavior of the brace is influenced by residual stresses and the initial geometric imperfection. So we included a longitudinal and transversal residual stress pattern to model the change in temperature during the manufacturing process of the tube. And then the initial geometric imperfection is modeled using a buckling analysis, including the first eigenmode where the nodes coordinate were scaled at L brace above 1000, as suggested in the Canadian standard. Also, the model replicates the boundary conditions of the grip used to secure the gusset plate. So here's a picture of the real, well, tested full brace. And we also use the same displacement-based loading that is applied in the longitudinal axis. For the mesh, a solid 20-node brick quadratic mesh element is used thanks to a larger deformation capacity and higher order shape functions compared to linear elements, for example. We also applied a finer mesh at the connection to achieve greater accuracy at this critical location. Finally, to conclude the assumptions for our numerical model, we find the fracture initiation of the brace when the equivalent plastic strain, which is called the peak, reaches unity at mid-length of the brace. This criterion is based on previous research on bracing members. So here's the result of the comparison of our numerical model and the tested brace in the lab. So here on the left, we have the specimen 12, which is the name of the full brace in the testing program when it fractured. And here's a visual representation of the numerical model at the same stage. So the criterion chosen to compare the finite element model to the test results is the force displacement relationship as presented in this graph. So the red dashed line being the response of the numerical model. So one can see that the finite element model can capture fairly accurately the inelastic response of the full brace tested in the lab. We can make some comments on this graph. The first observation is that the experimental test here in black exhibit a slightly stiffer behavior, which can be attributed to a different residual stress pattern compared to the numerical tests. We also have high buckling loads here that are observed, and that can be due to a different geometric imperfection that is implemented in Abacus. And lastly, although it is a good approximation, greater accuracy can be achieved if a proper better-suited material model with cyclic data is used. So now that we validated our model, we can move on to the second chapter of the thesis. So this section aims to assess the behavior of the gusset plate under cyclic loading and its impact on the performance of the connection based on several parameters. So for that, we created 21 different models while varying 4 parameters. So the first one being the HSS size. So we have 3 sizes here, the smallest one and the largest one. We also changed the length of the brace because it will influence also this global slenderness. So we have the shorter length and a larger length. We also have 2 different weld configuration. The first one is the A for the shortest one and B is for the longest one. And lastly, because we are interested in the hinge zone in the gusset plate during compressive cycles, we included an additional parameter that defines the shape of the clearance. So either linear here, elliptical here, or none at all, which is constrained here. So for the ID notation, E stands for elliptical and C is for constrained. So all models were designed using the suggested methodology by Afifi that I mentioned in the literature review. So for all 21 models, the mesh type, element, size, residual stresses pattern, and geometric imperfections are the same as the finite element model developed for the calibration. Except for the loading protocol, we've decided to choose a symmetrical protocol this time. So now we can move on to the results. So we have 4 types of results. The first one being the hysteretic force displacement response. So this graph shows the hysteretic response for the smallest HSS, but including all degrees of confinement. So the overall response is similar for all models except for the 1AC, which is in the black line here. So 1AC is for a constrained hinge zone with a shorter weld. And we can see that it has a higher buckling load compared to the other ones. So to understand where this difference can come from, I plotted the lateral displacement at their respective buckling load for the 1AC, 1BC, and 1AL1, which has a linear clearance. So we can conclude that a larger lateral displacement here at mid-length of the brace means also a larger rotation at the end of the HSS, thus reducing the actual force required to achieve that rotation. That's why here we have, because rotation is not permitted, we have a higher buckling load. Another interesting relationship to study is the moment versus rotation. So the moment is measured at the end of the connection here. So we have 2 graphs that shows all level of confinement configuration, one for the smallest HSS and one for the largest one. So again, the most critical model is the 1AC, which has the largest moment. So the one in blue. In the graph, the moment is normalized and all response never exceed unity, which is comforting. And also a permitted hinge zone, so either linear or elliptical in gray, so red and gray, exhibit the smallest moment in both cases, with a different shape for the largest one here. This suggests that a plastic hinge is forming in the gusset plate, enabling the moment to be transmitted beyond the brace. So to illustrate what we've discussed, here are two videos of a constrained configuration here on the left and a configuration with a linear clearance on the right. So it goes a little bit fast. Because there are no dedicated zone in the gusset plate for a hinge to develop, the rotation is forced to occur at the end of the connection in the HSS. We can see that clearly here. And for the right one, so we have a linear hinge zone here. So we can clearly see that the hinge zone develops in the dedicated 2TG here, clearance, which does not force the HSS to bend, but rather in the gusset plate. The third type of results is the peak versus drift. So the PEEQ is the accumulated plastic deformation. So I decided to capture the peak distribution at two critical loads, being the buckling load and the ultimate load for the most critical models, being the 1AC, 2AC, and 3AC. So they show two critical points, one here at the end of the tube slot and one here at the extreme fiber of the HSS. So the peak drift relationship is studied so for both locations. So the left one show all degrees of confinement for the smallest HSS. And as expected, the highest peak is achieved with the 1AC, which is constrained with a shorter weld. So the lines here show the peak measured at the end of the slot, but the star here shows fracture at mid-length of the brace. So what we can see is that the fracture at mid-length of the brace occurs before the peak at the connection reaches 1, which makes it capacity design protected. The right one, the peaks are much higher because the maximum stress is, of course, located at the extreme fiber at the corner. So at this stage, the approach used to define fracture initiation for this location might not be sufficiently accurate. So it leads to the conclusion that a permitted hinge zone, so either linear or elliptical clearance, is recommended in practice. So we can move on to the last type of results. So it's the von Mises stress distribution. So I chose to compare the 3AC and 3BE, sorry, because we can see that the difference is meaningful. So on the left, we have the stress distribution for a constrained configuration, where at multiple locations, the Fy is reached. We have, especially around the connection, some disparity in the distribution. And on the contrary, with an elliptical configuration, rotation occurs here in the gusset plate, so higher stresses are apparent in the hinge zone. But along the brace, we have much lower stresses compared to this one. So these graphs conclude the results chapter, and now we can go through a brief summary as a conclusion. So the first thing is that the force displacement showed that the 1AC, 2AC, and 3AC, so again, the constrained configuration with a shorter weld, experienced the highest buckling load, and a free hinge zone will exhibit a lower actual load. Also, these models reach the highest moment compared to the other configuration. The equivalent plastic strain revealed two critical locations, and their response showed that the connection is capacity design protected. A permitted hinge zone allowed to reduce the plastic strain. And finally, as a recommendation, based on what we found, I would encourage to design either with a linear or elliptical configuration, although a constrained gusset plate is also possible. But as we said, will lead to higher plastic strain, moment in the HSS, and also buckling load. So we also have a larger weld that will allow to have a better stress distribution. So with that, I can conclude. Thank you for the kind attention. And if you have any questions, you're welcome to ask them.
Okay, so thank you very much for this very interesting presentation. Then, as we said, please feel free to write questions in the discussion chat, and we'll address them at the end. Thank you. Thanks a lot. And then we move on to the presentation of Alexandre. Yeah, Alexandre, I think you can start, or is it frozen on my end, or does anyone?
Wait, sorry, I've forgotten to unmute me. So I'll start again. So hello everyone. My topic was investigation of collapse resistance in tall timber building. It has been done at the chair of timber structure in Zurich, under the supervision of two PhD students, one from ETH and one from the Polytechnico of Torino, for the support with the programming. So the topic, if it works, is dealing with robustness, which is defined as the capacity of the structure to limit the consequences of an initial damage. And collapses, or I mean, avoiding collapses is something we want definitely to avoid, but it's always in a situation where things go unplanned. So we have to deal with general concept or rules that we can apply to how to make things more robust. And for this, we need a collapse investigation software or tool, and that's what we did. We developed a simulation tool with finite element, where we can introduce initial damage and see the propagation of the collapse in the model. And for this, the goal is to assess timber buildings or various different timber building, and we will try to evaluate them or the performance with an index. And you might ask, why are we doing this in timber, especially? Is this timber is getting kind of a renaissance? We have higher and bigger structure that have been planned and built in the recent years. So as the building gets higher and bigger, then if something fails and collapses, then the consequences are also getting higher. So under the supervision of Alexandre Milliet, he started 2 years ago the development of a framework. So I was the third master student to do this on this topic and continue the development of this framework, which is actually programmed in Python with the module OpenSysPy, with a finite element module, which has been programmed open source, so we can see how it works and how we can implement it. And the good things about it is it is really fully parametric and really flexible, so we can use it the way we would like to. And it takes into account the geometrical and material non-linearities, and we can calculate everything dynamically. So in this framework we used and developed, we implemented a lot of specific features that we need for the purpose we're aiming at, so modeling collapses. So we're using something we call mixed element method, and it's the derivation of the finite element. And with this, we can try to separate element through algorithm if something fails. And we have also an element removal algorithm to introduce all the damages that we want to model. That's the key point, that the start point of the collapse when something is broken or something disappears from the structures. And we have also a lot of features based on really the failure. So when something fails, then we will track it and see how it fails down, and probably at some point it will impact an element below, and then this element might be or might break due to the energy of the falling element. So that are things that has been implemented, they are working, or we have to expand it as the software is getting bigger and that we or for specific purposes. And what is important to say, we can model any type of structure based on an orthogonal grid. So we have this grid where we can choose the span of each beam in both directions. We can also introduce trusses to stabilize the structure. We are working on shells and walls to implement it as well. But for the moment, as I finished my master thesis, this was not going perfectly. So I just let them aside and work only on the trusses and the rest of the connection and so on. And you see here, this is an example of something we can program and use and try in the software. So now just to explain how the mixed element method work, the principle is really simple. We have our finite elements, and between those, we always have rigid links. These rigid links are just there to get deleted if the resistance at this part of the structure is exceeds. I mean, if the internal forces are higher than the resistance. At this point, we can delete those links and the structure will behave further. And the good things about this is that we don't have a stability problem because the number of nodes in the structure remain the same. So the matrix size for all the calculations stay the same, just the value differs at this stage. So when we see the example of a simply supported beam, as we have plenty in the structures, the circle are not hinges, but just nodes. We see really that we have each beam element, and between those we have finite these rigid links. And what is also important is timber is not really massive or not connecting clamped with the other part of the structure. We always have a connection, and these connections are modeled also through a link between the many support or any other element like a column. And these connections are really a key of how the structure will behave. So we have to model this, and this is something that we implemented in the software. So all the beam to column connection are modeled with a dowel connection where we have steel plates that are going from the column to the beam, slotted into the beams, and then we have dowels inside the steel, making as a shear transfer the connection. And this dowel connection, depending on how it is constructed, might reach a moment rotation relationship. So we can have a moment resistance. It won't not be clamped, it's not rigid, but has like a half rigidity. And this is something we modeled through an hysteresis in the model. So then, after all the development has been done, we tried to use a simple model to see what the result we can get. So the model we used was a two-story frame building, double symmetric to make it easier, with a story height of 3.5 meters and span of 4 meters. We always use glue laminate timber GL24 for those. It should be representative of higher structures, but just due for computation time constraint, we reduce the size of the problem. What is important to mention is in high-rise of timber high-rise, we mostly have a column that is continuous over many stories. And this is been done because it has a better property of the timber in the longitudinal direction for the vertical load. And we connect all the beams through a connection to the columns. So we mostly have a simply supported beam that are not clamped, but not simply supported either, but with this connection, we can have a half rigidity. In this model, we would like to try many variations of it and see what are the main properties that are important. So we can still define the beam cross-section with the height and beam. The width can be freely chosen. The connection can also be chosen freely with the number of dowels, their diameters, the number of shear plates, and so on. And the column cross-section, which is squared, just to respect the double symmetric. And so we created with this model, these parameters, a pool of structure that we then run through the simulation and see how they behave. And so first we set all the parameter range for all those beam and connection parameters. And the things is we would like to have only realistic building, because it might not be important if the structure cannot be built either, so it won't be robust, but yeah. So we just loop through all the combination of the parameters we have and just only sorted out the realistic combination just to assess them. So we make a design with the ultimate limit state and service limit state with a normal load case, with a self-weight, a dead load, and a live load. And the things we don't only want to match the minimum requirement, but we don't want to have an over-designed structure as well. So we just keep a range of things that are possible. If the beams is really enormous, then it won't be built because it's not economical. So we just use only the 50 model that we consider as realistic. And then with this 50 model, we run them with an initial damage, which was set as a column removal, which what we have seen that there is 3 end cases where we remove the corner column, the edge column, and the inner column. And at this point, when we have a damage, we are in an exceptional load case. So we use other factor for the load in the software. Just to explain how the simulation work is, first, when we start the simulation, we calculate the internal forces and the displacement of the structure in a static way, just to see if it can still wear all the load we have. And then at the time 0, we remove a column and start the dynamic analysis. And at this point, we do 2000 time step of 0.5 millisecond to cover the response as the most realistic way, with having really tiny time step. One simulation on a good computer for the simple model took 2 to 3 hours. So when we run the 50 model with the 3 scenario, then it takes a lot of time. And why it takes so much time is because we are doing checks at every time step of the internal forces. And if the resistance doesn't match, then we do the separation of the elements, check if something is falling. And also we do at each time step a new model analysis just to implement a new model damping for the structure. So we just update the model damping at each time step if the structure just get separated or just evolves. And then when we had all our simulation with all the data it provides, we try to assess all the results. And the performance index was not so easy to explain, so I just explained to you the principle. So we express everything in cost, where we first consider the cost of the construction of the structure, and then submit the event cost of each scenario, where the event costs are the cost to replace the structure, or if some part have fallen, but also societal costs, because if the structure falls and people are inside, then there will be injuries and death, and those are costs to the society. So we also consider them just to make things a bit realistic. This can be criticized, and it was criticized also from my side, but never mind, the numbers doesn't matter in these terms what we use, because the results are kind of clear. So just remember that the performance index is, the results are better if the number is lower. So then now I present to you the results. So we rank it all our model based on a scale from the performance index, and we really see clear trends. So where we have a couple of models behaving really in the same way. And the thing is it's more a problem of if the structure fails or not. And there is no really differences in structure if some fails a bit, but not all, not the wall structure and so on. And we really see that the group on the right, they fail in every scenario. And then group on the one group on the left a bit, they can withstand the corner column removal. And then we move further to the left, then they can withstand the two scenario with the edge column and the corner column removal. And then the two models on the right, on the left, they withstand all three scenarios. So this is basically the result. And the important things about this is we have to know why those structure fails and some of them don't. So just to improve the structure and find rules to design structure in a more robust way. And so we just have seen in, for example, in model 9, which falls in every scenario, they all have a partial collapse. And so why this scenario, this model? And then compared to the model 22, who just displays a bit and just survive in all three scenarios. This is something we took a look. And this is probably the most complicated slide, but just know that we have a lot of data, so we just looked inside, and this is both model 9 and 22 for an inner column removal, where we looked at maximal normal shear stress utilization in all elements. So we just calculate the element that is the more loaded in this structure at each time step, and just look if something will fail. And we just see that, for example, in model 9, the highest point is 0.5. So the structure doesn't fail because the elements are not big enough, and neither the model 22. But if we look at the connection, we have also all the data about rotation capacity utilization in all the connection. And we just see that it increased quite sharply after the removal, and reach fast enough in the plastic zone. And at some point where we reach 4 times the rotation capacity, the elastic rotation capacity, we just said this was big enough and then break. So we just see the difference between the model that survives and the model that doesn't is that the connection is not stiff enough and just rotate too much until it breaks. So then we went in all the results compared with the stiffness of the connection, and we really see the clear trend that if the structure has a connection that is stiffer, it has higher chances to withstand all the removal. And with this, it is normal because we have a link between the stiffness of the connection and the moment resistance of the connection. So as the connection is getting higher, we can withstand higher moment, so we can redistribute the forces in a better way. And after this, we just started to look if simple trusses in the structure can also help to redistribute the forces, because at the previous stage, the structure was not stabilized. It was only a frame. And now we just looked at a 3-truss system and make a new simulation with those, where with the trusses were 200 millimeter of size. And we'll perform also the true simulation, and we just have seen that the trusses can really help redistribute the forces and help withstand some scenario independently of all the other parameters we use for the beam cross-section, connection, and so on. And this is really the keyword, because in some in timber high-rise structure, we will have trusses to stabilize horizontally, or maybe even have an outrigger made of trusses to stabilize all the forces, and this can really help the structure in those exceptional situations. So as a conclusion, it was really the things we would like to be robust, we have to have redundancy. And in those examples where we looked with the software is either we can have a stiff beam connection that can have then a moment resistance instead of a simply supported beam, or we can put trusses. And the results are kind of understandable and obvious, I would say, because we didn't realize at the beginning if the connection is really it's not stiff, even almost a hinge, then as soon as we take columns, then it moves as a mechanism. So it is kind of obvious that we have to introduce a stiff beam connection or trusses to reduce forces. And what is also important to say is the software is in continuous development, and there is another student right now doing the same master thesis and developing it further. So they will have different and new feature coming on and new investigation with it. With this, I'm finished. So I'm just here to answer your question.
Yeah. Thank you very much to both of you for these really interesting presentations, and well, also congratulations once again for the excellent work that you've done in your thesis. So do we have any questions? You can again, you can write in the chat, or like either with a virtual hand, or raise your hand, or turn your camera on. If there are any questions. If not, maybe I have one for Joëlle. I mean, I thought it was quite interesting, the construction. I have to admit, I'm not all too familiar with all the different steel type connections, but if I understood well, I mean, it's an improvement of a braced connection. Do you think that would be sort of thinking of potential developments or usages in Switzerland, do you think that could be a construction in bracing detail that's useful in the Swiss context also, like maybe especially in higher seismic zones or anywhere, like where could be the advantages of the system or the connection type?
Yes, we're currently working on writing a paper, so we can then add some rules in the Canadian standard. So maybe first in Canada or USA, but then the last chapter of the thesis is about constructability. So it's very interesting to know that it works technically, but now we have to see if it's possible to construct on site. And so we're still working on that, but if the results are good, then I don't see why it cannot be constructed in Switzerland.
Thank you. And then maybe also a question for Alexandre. I mean, it's quite interesting. I think you talked or investigated the collapse propagation in general. Do you think the framework, if I think about seismic design or assessment, do you think it might be useful to improve seismic design or assessment, like to create the right redundancy, so to say, and not create redundant elements where they're not useful, but sort of optimize the design or assessment of existing structures?
The other things about this software is really interesting because we can, in theory, also use it for seismic design, because we can also introduce a spectrum of an earthquake and see how the structural response. Then, if we want to use it in a practical application, the problem will probably be to model the structure we would like to build as it is really in reality, because we are kind of in a general state where we have general assumption and we try to model it as many structure could be and not really in one specific term. So it can still be but then we will probably to program things in a different manner if we would like to cover something specific.
Okay. Yeah, thank you very much. Are there any other questions? I think there's nothing in the chat, if I see correctly. I don't see anyone raising their hand. So yeah, if there are no more questions, I think we wrap it up. So thank you very much again to both of you for taking the time to present your excellent work. It's really interesting to learn more about this, and then we'll all the best. Let's hope the tests go well, the construction tests. So yeah, we're looking forward to following that and have a nice, or I mean maybe one or two more announcements for the SGEB. So the next seminar, if I'm not mistaken, is on March 1st, 3 p.m. Where the people that participated, I think we have one member here who participated in our reconnaissance mission in Morocco, will present their findings and what they saw on site. So it's also for those of you that are SGEB members, you saw it in the newsletter, and I will also it's on the website as well. I'll also announce it on LinkedIn again. So I hope to see you, some of you at least, for that, and have a nice day, everyone, and bon appetit for those that still eat. Thanks a lot.
Thank you. Have a good day.
Thank you very much for having us.